Assalamualaikum warahmatullahi wabarakatuh. Today we are going to learn two chapters, which is chapter 12 and chapter 13. Chapter 12 is related to the instruction sets, characteristics and functions, while chapter 13 is the instruction sets focusing on the address modes. My name is Dr. Nur Azura Zakaria and I'm from Department of Computer Science, KICT. We are going to see what are the learning objectives for this chapter. The first learning objective is you are able to present an overview of essential characteristics of machine instructions. The second learning objective is you are able to describe the types of operands used in typical machine instruction sets. And the last one, you are able to describe the various types of addressing modes common in instruction sets. So what are the contents or topics for these chapters? For chapter 12, we are going to learn on the machine instruction characteristics, types of operands, and also types of operations. While chapter 13, you are going to learn different types of addressing modes. However, I'm going to touch further on machine instruction characteristics and also addressing modes. For the types of operands and types of operations, this one is very much theoretical, so you can read from the slides. This is the first topic, which is the machine instruction characteristics. We are going to see this one basically is the instruction cycle state diagram, and this one you already seen from chapter 3. The operation of the processor is determined by the instructions it executes. It is referred to as machine instructions or computer instructions. So the collection of different instructions that the processor can execute is referred to as the processor's instruction set. And these instruction sets basically contains a set of binary numbers. Each instruction must contain the information required by the processor for execution. So we are going to see what are the machine elements of the machine instruction. We are going to see what are the elements of a machine instruction. So basically there are 4 elements in the machine instruction, which is the operation code, source operand reference, result operand reference, and also next instruction reference. So we are going to see what actually the description in each of the elements. So for the operation code, basically this is also known as the opcode. In the operation code, it basically specifies the operation to be performed. For example, addition, multiplication, subtraction, jump, and so on. The operation is specified basically in a binary code, and this is also known as the opcode. So basically, the machine instruction will be instructed to do this. What actually do this? This is the operation or instruction that need to be done by the machine instruction. For example, the addition, multiplication, and so on. The second element is the source operand reference. So the operation may involve one or more source operands. Operands that are inputs for the operation. So basically, operands are also known as a data. So the operand basically inputs for the operation. So basically, the machine instruction will take these operands to do some performance or to do some operation. The next machine instruction is the result operand reference. So the operation may produce a result. So in the machine instruction itself, it already assigned the result operand reference. So the result will be put inside the assigned location inside the machine instruction. The last one is the next instruction reference. What does it mean by next instruction reference? It tells the processor where to fetch the next instruction after the execution of this instruction is completed. So after you have done that, then do this. So basically the machine instruction will receive this kind of instruction After you have done that, then do this. For example, after you have done the addition process, then you need to do the multiplication process, right? So this is the simple machine instruction. And basically, the programmer needs to know how many bits should be inside the machine instruction, because inside the machine instruction, it only has the binary bits, binary number. Remember that our computer is only operates in the binary numbers. So inside this machine instruction, it only has the binary numbers. So it has a specific, or it has a number of bits inside the machine instruction. So basically, the programmer must know how many bits for each of the machine instruction. For example, here it has three categories here: the opcode, one operand reference, and second operand reference. So for example, if the opcode is 4 bits, so how many bits for the other operand reference that can be placed inside the machine instruction? So the whole machine instruction, for example, is 16 bits. So meaning that if the operand reference has the same number or same length of binary numbers or binary bits, so meaning that after this opcode 4 bits, 16 minus 4 bits, so meaning that you need to have equal number or equal length of the operand reference. So in this example is 6 bits. Both operand reference has 6 bits. So this operand reference, it can be either source operand, either results operand, or the next instruction reference. So these basically are inside the machine instruction. This one is the operation code or opcode, and the rest can be a source operand, can be result operand, or it can be next instruction reference. We are going to see what are the category of the source and also results operand. There are 4 categories of the source and results operands, which is the main or virtual memory, processor register, immediate, and also input-output device. So for the main or virtual memory, the address of the main or virtual memory is located inside the instruction, machine instruction. Remember in the program execution, whereby the address of the main memory is inside the instruction, and when the instruction is executed, it will obtain the value that pointing to the address of the main memory. So basically, that's the idea of the machine instruction for the main or virtual memory. The same thing goes to the processor registers. So a processor contains one or more registers that may be referenced by machine instructions. So basically, the machine instruction will receive or must contain the number of the desired register. The next one is the immediate category. So inside this, in this category, the value of the operand is contained in a field in the instruction of being executed. So basically, this one is a difference from the main or virtual memory and also processor register. In the immediate category, the operand basically is inside the instruction. It's not pointing to the addresses, but the value of the immediate category is basically inside the instruction. So basically, this one you will learn more in the next chapter, which is the addressing modes. The next category is the input-output device. So the instruction basically must specify the input-output module and device for the operation. If a memory map input-output is used, this is just another main or virtual memory address. So if the machine instruction needs to obtain operands for the input-output device, so this input-output device must be specified inside the machine instruction. Next, we go to the instruction representation. So this one, the instruction representation is one of the machine element characteristics. Basically, in our computer, instruction is represented by sequence of bits because our computer can only understand in binary numbers. So there are several sequence of bits inside our computer to execute or to perform certain instructions. Same when you do the programs or programming. So basically, you will specify one by one or sequence of the instructions. So basically, what you did is the high programming languages. So that programming languages will be translated into the will be compiled by the IDE or compiler, and then it will be translated into the machine languages, which basically is understood by our computer, right? The instruction is divided into several fields corresponding to the constituent elements of the instruction. So these are the instruction format, and this instruction format is segregated or divided into several fields. These are the examples, or before that, opcodes are represented by abbreviations called mnemonics. So these are the examples of the mnemonics or the opcodes. For example, add means that this is for the addition purposes, addition instruction, or addition operation codes. Sub is the mnemonics for the subtract operation code and others. Basically, there are many. If you are going to majoring into computer science later on, you are going to learn the computer assembly and architecture languages. So inside Chap12 courses, you are going to learn how to do the practical codes or how you want to program the assembly languages using the right compiler. If I'm not mistaken, is the Mars. So Mars will be used in the Chap12 course later on. Okay. And the operands are also represented symbolically. Each symbolic opcode has a fixed binary representation. So the programmer specifies the location of each symbolic operand. Now we take a look at this example, the program which is x equals to x plus y. So based on this program, we understand or we know that this is the addition process of x and y, and this addition, the results of this addition must be assigned in the variable x. So there are differences between high-level languages and also the machine languages or low-level languages, for example, the assembly language. Inside the assembly language, you need to list the, or you need to declare the address of variable x, and also you need to declare the address for variable y. For example, here x, the address for x is 513, meanwhile the address of y is 514. So these are basically the instruction, okay, the instruction that must be performed to do this program. All right, the first one, you need to load a register with the contents of memory location 513, and then you need to add the contents of memory location 514 to the register, and then you need to store the contents of the register in memory location 513. And this is the illustration or the diagrams are based on this instruction. So you have the memory location and you have the register location. So inside the memory, you have location or address for X and also address for Y, 513 and also 514. So the first instruction, you need to load the value inside 513, or you need to load the X inside the register. And then you need to take the value inside Y and you do the operation addition. And then the value or the results after the addition process, you need to store back inside the memory X. All right. So basically, this one is similar like the program execution that you learn inside chapter 3. And these are basically the instruction inside the low-level programming languages or machine instruction. If you can differentiate the high-level languages and also the low-level programming languages or machine language, basically inside the machine language, you need to specify one by one the operation or the instruction. But inside the high-level languages, the instruction is lesser compared to the machine language instruction. So what basically the instruction that we can do inside the machine language programming. So basically these are the instruction types. We can do data processing, we can do data storage, we can do data movement, and we can also do the control. So inside the data processing, it's very much on the arithmetic and logic instruction. You do the addition, multiplication, and so on. And inside data storage, basically it is a movement of data into or out of register and or memory locations. And the data movement, the input-output instructions are needed to transfer programs and data into memory and the results of computations back out to the user. And the last one is the control. Basically, it can do on the test and branch instruction. Next, we are going to see the number of addresses. Start from 0 address instruction, 1 address instruction, 2 address instructions, and also 3 address instructions. So these are the examples of the machine instructions or assembly languages for this program. Okay, this is what we call as the opcodes, and this is the symbolic operands. For those who are going to majoring into computer science, you are going to take Chap12 courses. Chap12 stands for computer architecture and assembly languages. So inside this course, you are going to learn how to code using Mars IDE. Okay, so you are going to learn further on how to create the machine instructions using the assembly languages. We go to the 0 address instruction. So this is the instruction format which contains only the opcodes for the programs. This is the example of the programs to be executed. The first rules inside the 0 address instruction, you need to change these programs to the postfix notation. How to change the postfix notation? All right, so the postfix notation, basically you have the variables, and then after the variables is the operation. Okay, so this is the meanings of the postfix notation. You have the variable in front and you have the operation at the end of the variables. Inside the 0 address, this one is also called as the last in first out or LIFO. Okay, so this is the example. Okay, the last in, the last stack is the first things to out, right? And the opcode for the 0 address instruction is the push, pop, and also top of the stack or toast. Alright, so how you want to do the 0 address instruction, you need to scan from top to bottom and also left to right. If you have a fraction programs, so you need to scan from top to bottom and from left to right. But if you have the normal programs which do not have the fractions, so you just scan from left to right. And then you must follow the BODMAS, right? The bracket, orders, division, multiplication, addition, and also subtraction rules. Alright, so for these programs, what is the postfix notation? The postfix notation, as I mentioned before this, you need to have the variable in front, and after the variable is the operation. So from here, you can see that the postfix notation is AB, and then minus at the end of the AB, and then you do the C, D, E, and then you followed by the multiplication, because you need to do the operation inside the bracket first, and then you do the addition, and after that you do the division. All right, so this is the postfix notation: AB minus CDE multiplication, addition, and also division. So this one AB, and then AB, you have the minus operation at the end of the variables A and B, and then you do CDE, right? And then you do the multiplication first, you do the addition, and then you do the division. All right. So basically, this one is very much, the code is very much done by the programmer. Right. So this is the instruction for the zero address, and this is the comments. So basically, this comments is visible to the programmers to give meanings to the instruction. Right. So the first one, after you do the postfix notation, right? So you need the instruction you only has the push, pop, top of the stack, and also the others opcodes. For example, subtraction, multiplication, the operation, all right? And then from this postfix, right? You push A, right? And then push B. So top of the stack is A. After that, push B, top of the stack is B. And then you do the subtraction and push C, push D, push E, right? And then you do the multiplication, you do the addition, and then the last one, you do the division, right? After that, you need to pop Y. So after pop Y, the command is Y will receive top of the stack of the zero address instruction. So these basically are the stack, right? And the zero address instruction, it also has a pointer. All right, the pointer refer to the top of the stack. All right, so this one we call it as a last in, first out. Right, so the first one, the last one will be the first one to be popped to the Y memory. All right. So this is how you do the zero address instruction. You have the instruction, and then this is the comments which visible to the programmer to understand better what are the instruction. Another option that you can derive the postfix notation is from the expression tree. So you can find the video on the expression tree, the demonstration on how to build the expression tree inside this lesson. Now we go to the one address instruction. So this is the instruction format for the one address instruction. It contains the opcode and also the operand, right? And this is also the same programs to be executed like zero address instruction. Inside one address instruction, it has accumulator. The opcode for one address instruction, it has load and also store. Load means that you need to load value from memory to accumulator. For store, you need to store value from accumulator to memory. So this one is different from the two address instruction. All right, this is the opcode that need to be used for the one address instruction. And inside one address instruction also, you need to follow the BODMAS rules. If you have fraction program like this one, it is advisable to start with the denominator because this one is much more easier. But you can also start from the top one, all right? But it is advisable if you can start with the denominator. And this is the instruction using the one address. Okay, you have the instruction here and you also has the comment, right? And the first one, okay, this example, we start from the denominator, right? And we must follow the BODMAS rules. So we must use, or we must do the multiplication because the multiplication is inside the bracket. All right, so we need to load D. Inside the comment, basically D value in D is loaded inside the accumulator, right? And then we do the multiplication with E. So inside the accumulator, right, the accumulator multiply with E, right? Because inside the accumulator, the value inside the accumulator itself is multiplied with value from E. And after that, we do the addition with C. So this one, so this one is C. All right. So accumulator, okay, accumulator add with C value, right? And after that, we need to store the AC into Y because we need to do the other operation, which is A subtract to B. If we do the subtraction inside the accumulator, so it will be a wrong instruction because the accumulator must do the denominator first. After that, the results for the denominator will be stored inside the y. Then the accumulator is empty. We can do the operation A subtract B, right? So after we store the value inside accumulator to Y memory, so the accumulator is empty now. We can load value of A. So inside accumulator, it will receive value of memory A, right? And it will do the subtraction. So the AC subtract B, and after that, the last operation is the division, right? So the accumulator divide with the value of the denominator, which we stored inside the Y memory. So AC divide with Y. And after that, we need to store all the results inside the Y memory. So Y memory will receive the value from the accumulator register. Right, so this is how you do the one address instruction. Okay, the instruction using the one address. The next one is the two address instruction. This is the instruction format for the two address instruction, whereby it has opcode and it has two operand here. All right, operand 1 and operand 2. And this is the programs to be executed, the same one. Inside the two address instruction, you can have temporary registers. You can have multiple temporary registers. Compared to the one address instruction, you don't have many registers, but inside two address instruction, you can have multiple temporary registers. And inside two address instruction, you need to use opcode move. Okay. Inside two address instruction also, you need to follow the baud mask rules. And this is the instruction. And this is the command using two address instruction. Right? So the first one, you need to move value inside A into the memory Y. So move YA. So Y will receive value from A. After that, you do the subtraction, sub YB. Inside Y, you do the subtraction. Y, because Y already contains value of A, so Y minus B. Right? After that, you use temporary register. You move value of B inside the temporary register. All right. So you move TD. So inside temporary register, you receive the value of D. After that, TE for the multiplication operation. Inside temporary register, it do the operation multiplication. So basically, inside the temporary, it already has value of D. So T multiply with E. Right? After that, you do the addition with C value. So inside the temporary register, you do the multiplication with C value of C. So this is the comment T plus C. After that, the last one is to you do the division. So you need to do division, all right? Y with temporary register. Right? So Y will receive the value or results of the division. Y divided by T. Right? So basically T is already has value of the denominator and Y already has the value of A minus B. So you do the division Y divided by T, and this is how you do the to address instruction. The last one is the tree address instruction. This is the instruction format. It has the opcode in, and it has also three operands here, right? And this basically refer to the three different addresses for inside the memory. Okay, either main memory or the registers. So inside three address instruction, it can has a temporary register, and you must follow the baud mask rules. Alright, and the instruction, this is the instruction and the comments. So the instruction, you start from the top one, sub YAB. So means that memory Y will receive the results of subtraction of A and B. So this is the comment Y A minus B. So the results will be stored inside Y. The next one, multi-DE. So you use the temporary register to do the multiplication of D and E, right? And this is the comment. Inside the temporary register, the same temporary register, you do the addition, all right? Add TTC. This is the opcode add, and these are the operands TTC. It refers to the 1, 2, 3 address, right? And this is the comment T receive the results of the addition. T basically already contains the value of multiplication here, D minus E. After that, it will do the addition, right? And the last one, you do the division, whereby memory Y, okay, memory Y receive the results of the division Y and temporary register. Okay, so this is the comments. Value of memory Y receive value of the division Y and T. Alright, so basically three address instruction is much more complex compared to the one address instruction because it refer many addresses compared to the one address instruction.